internalize this, so where we first encrypt a message using an encryption scheme with the key KE, and then we authenticate the ciphertext using a message authentication code with a key KM, and the output then is C, T. And so this is only the only really secure things. We looked at rejecting ciphertext, and then the important. So this is then the more formal way of describing this. So the key generation now generates a key for the encryption scheme and the key for the message authentication key, and then we encrypt and authenticate. And the verification, it first checks that the tag T is a valid tag for the ciphertext. If not, it outputs a failure symbol. Otherwise, it really decrypts the ciphertext and gives you back the message. Okay, so if the ciphertext does not verify using the tag, then you just output this failure symbol. And then we first defined unforgeable encryptions, authenticated encryption, and then we want to prove that authenticated encryption yields CCA secure encryption schemes. So unforgeable encryptions is similar to the unforgeability game in message authentication codes, but here the goal of the adversary is, given an oracle or given the ability to ask for encryptions, to come up with a new valid ciphertext. Okay, and if he wins that game, if that ciphertext first of all decrypts to a message that's not the to a legitimate message, and it's a new one. So unforgeability of encryption means that you cannot create valid ciphertext yourself. The only way to get valid ciphertext is sort of ask your encryption oracle. And then we defined an authenticated encryption scheme as one that is CPA secure and unforgeable. Okay? And the last thing that we did last week is to show that if pi is, so the encryption scheme that we use in encrypt and authenticate is CPA secure and the message authentication code is strongly secure, then this construction of encrypt then authenticate gives us authenticated encryptions. And we only proved that, so the CPA security is an exercise, and we only proved that it has unforgeable encryptions. One has to be a little bit careful about CPA security, because now we also get not just the original ciphertext in scheme pi, but we also get tags. So we have to make sure and have to prove that the tag don't give you any additional information that help you to win the CPA game. Okay. Now comes the big theorem that we want to prove today, and that's the only goal for today's lecture, basically. Prove that if an encryption scheme is an authenticated encryption scheme, then it is actually CCA secure. So no adversary has a non-negligible advantage in distinguishing between ciphertext for messages of his choice, even if he has access to an encryption oracle and access to a decryption oracle. Okay. Yep. Should we go back to CCA security, or you have encryption oracles, you have decryption oracles, you have the usual distinguishability requirement. The only restriction for the decryption oracle is that once you get your challenge ciphertext, you are not allowed to ask for the decryption of the challenge ciphertext, otherwise the whole thing would be not very useful. Okay, and then we can conclude that if pi, the original, if we use encrypt then authenticate with the CPA secure encryption scheme and the strongly secure message authentication code, then by theorem 5.4, it's in an authenticated encryption scheme. So then by theorem 5.5, encrypt and authenticate leads to CCA secure encryption schemes. Just the combination of these two theorems. And that is the, as I said, CCA security, that's the ultimate goal of encryption schemes. That's what we really want to achieve, CCA secure encryption schemes, and then we have constructed those things from CPA secure encryption schemes and message authentication and strongly secure message authentication codes. And we'll, at the end, I will just summarize what are the assumptions now that we need to make to get to CCA secure encryption schemes. Turns out the only thing that we need is one-way functions, basically, or pseudorandom functions. Okay, good. So let's go to the proof of theorem 5.5. Huh? So, here is first an outline of the proof. So first we go back to the CCA security game, and we modify it a little bit. And we call the modification RCCA game. And the modification is that, remember, games are always between, or experiments are always between adversaries and challengers. And in the RCCA game, the challenger always answers decryption queries with the invalid symbol. So he just basically ignores the decryption queries and just says, oh, everything's invalid. So that's a modification of the game. The game is not interesting in itself. It doesn't lead to any interesting security notion. It's just for the proof. It's a thought experiment for the proof. Okay? And we define valid queries as decryption queries that are not answered with this failure symbol. And then what we will do is we define a random variable, VQ, a pi of n, that indicates whether valid queries occurred or not in this game or in this game. Notice that in this game we can also define a valid query. It just gets answered differently. In fact, it gets answers, in the sense of this game, it gets answers incorrectly, because it should get the message and not the invalid or the failure symbol. Okay? So we can do this thing here for both games. And then what we show is that the difference in probability that A in the CCA game with this authenticated encryption scheme outputs 1, and that it outputs 1 in the RCCA game, this difference in probabilities can be bounded by the probability that this random variable is 1. Okay? So we'll move from one game to another, and then we'll estimate or bound the probability, the difference in probabilities in the two games. Then what we will show is that this thing here is negligible. And we show that in this RCCA game, the probability that A against pi outputs 1, that is wins, minus 1/2, is negligible. Here we use the CPA security. Here we use the unforgeability of the authenticated encryption scheme. Okay. And then, as we'll see, and then the result will follow just applying triangle inequality. We'll do that basically the first thing in the proof. The proof uses two new proof techniques. The first one is, these are very new slides, so if you have old ones, they may not be up to date. So this the proof uses two important proof techniques. The first one is called game hopping and the difference lemma. The second one is index guessing. And so what are these things about? These are two of the most important techniques in cryptography, in proving security. In particular, game hopping is for every, I would say every more complicated security proof in cryptography more or less uses this technique almost. So what we do in game hopping is we want to analyze one game. In our case, the CCA security game. Yeah? But that's too difficult for us. So what we do, we replace it by a different and easier to analyze game. Okay? But then obviously we have to relate the two games. I mean, this is easier to analyze, it's nice, but what does that tell us about the original game, right? So then what we do is that we argue that the difference in success probabilities between the two probabilities is very small, or we analyze the difference in the two success probabilities. And we use that using the so-called difference lemma. Okay? And that's exactly what we do here, right? We want to analyze this thing, it's too difficult. We analyze this, well, actually we want to analyze this here, too difficult, and instead we analyze this here, but then we have to analyze also the difference in probabilities. Okay. And so the difference in probabilities is based on a very simple lemma, the difference lemma. But then we have to, that relates these two probabilities using another event, and then we have to analyze that event. Okay? Often these things are done sequentially. So you hop from one game to the next, then to the next, then to the next, then to the next, then to the next, and so on, until you eventually end up with a game you can analyze. And then what you do is you analyze always the difference between two consecutive games. The reason you do that is because you want to make sure that you can always analyze the difference between the successive games. So you always do small modifications so that you can analyze these small modifications instead of analyzing one big modification. Yeah? So that's the technique that's behind this. And as I said, we use that in this CCA game and RCCA game. But then we have to analyze also, in our case, this probability here. Okay, and for that probability, we use another important technique that's called index guessing, the index guessing technique. And this technique, in general, does the following. We want to simulate adversaries, and we want to guess when a certain event happens for the first time. Okay? So going back to this case here, when we analyze these games, or when we analyze this guy here, this game here, what we would like to know is when does the adversary for the first time query something that is valid, but where in this RCCA game he gets the wrong answer if we would look at this game. Okay? So when does he pose for the first time a valid decryption query that gets answered incorrectly with the forgery symbol? Incorrectly if we have the CCA game in mind. So we want to guess that particular query, the first one. And then what you can argue is that up to that point, if you go back again to this thing here, up to that point where for the first time the adversary poses a valid decryption query, the two games are exactly identical. Because up to that point, these answers, invalid, are correct, are exactly the same answers as the adversary gets in this game. Okay? So up to that point, everything's fine. So in particular, the probability that this is the first query at which this happens is the same in both games. But then we know that, if that event has happened, then the adversary has queried a valid decryption query. But then a valid decryption query exists. But we assume that the scheme has unforgeable encryption. So that will lead us to an adversary against the unforgeability of ciphertext, because then we have a valid decryption query. So in more general form, up to that point, the simulated and real adversary get identical distributed inputs. After that point, we have no guarantees, but the event should be useful for our reduction. In our case, the event is exactly what we are looking for, namely the forgery of a ciphertext. The point that we want this thing, the point where that happened for the first time is because up to that point, the two games are identical. Up to that point, we don't know. In our case, then, basically the RCCA game is like a CPA game, right? If you always answer with failure, you may as well just throw out the decryption queries as well, because the adversary can generate the failure symbol all by himself. Okay. The details will become hopefully clearer in the proof. Okay. So let's go to the details, unless there are questions. Okay, so then let's go to the CCA game. Just to recall, what is a CCA game? Between I, A, and pi, where pi is, in our case, an authenticated encryption scheme for our proof. Here's the challenger, here's the adversary. Both get the security parameter as input. The challenger generates the key that is used. The adversary can pose encryption queries and decryption queries and gets back the correct answers. Eventually, he outputs two messages, usually if of the same length, but never mind. The challenger picks B from 0, 1, encrypts the message MB, sends over C. The challenger, the adversary can again answer a query, ask for encryption and decryption queries, except for this guy here, and gets the correct answers back and outputs a bit B prime, and he wins if B is equal to B prime. Now the RCCA game, every decryption query is answered with the failure symbol. It's just a thought experiment, not a useful game. Here failure, here failure. But of course, we can again define the probability that A against pi in the RCCA game outputs, wins the game. That is, B is equal to B prime. Yeah. Okay. So simple modification. Now let's define these valid queries. And what we assume, it's just a simplification, we assume that A never asked the decryption query DAC case CJ where CJ was obtained by an encryption query. If A does it, replace it by an A that does not do that, because he already knows the answers. It's a PJ, right? If CJ was obtained as an encryption query, just answer with PJ. That was your own query. So it's not useful for him anyway. And that is maybe, if it occurs in the CCA game for A, then it also occurs from the CCA in the RCCA game, say. And as I said, we call a decryption query on ciphertext CJ valid if the decryption gives something different from the failure symbol. And we denote by VQA pi of n the 0, 1 random variable that is 1 if A asks a valid query in the CCA game. Okay? And it's 0 otherwise. So for each run, you can check the internal randomness of the challenger and the and the adversary. You can see whether over the choice of the key K over the internal randomness of the challenger and the adversary answers poses a valid decryption query or not. And it's really over the randomness. Randomness is used here. It's used here, computing these things. It's probably used in the encryption. Right? Eventually, we assume that pi is CPA secure, so it will be randomized. It's probably randomness used in the computation of M0, M1, and then it's used here, and it's used here in the computation of the encryption. So there's lots of random choices made, and for given random choices for one game, we say that it's a success, or it's one if that with these choices we have a valid decryption query. Okay. And we assume, again, for simplicity, that on 1 to the n, A asks exactly Q of n decryption queries, where Q is some polynomial. Actually, Qn is an upper bound, but then let him ask for a few dummy encryption queries if it doesn't meet the upper bound. Okay. And then we define J, additional encryption random variables, VQA pi j, comma n, which is 1 if the J decryption query is A's first valid query. So VQ1 is VQA pi 1 is 1 if the very first decryption query is already valid. VQA pi 2 of n is 1 if the first decryption query is invalid, but the second one is valid. VQA pi comma 3 is 1 if the first two decryption queries are invalid, but the third one is valid. Okay. What we'll use is that this random variable is a disjoint partition of these. There's always just the first time, right? And that first time is unique. That will help us in analyzing these things. Okay. Let me skip this difference lemma for the time being. Okay, so now what we prove is the following. We first will prove that, as I said, the probability that an adversary A wins the RCCA game against an authenticated encryption scheme -1/2 is negligible. First thing that we prove. Then we prove, as I said, that the difference for all adversaries A and all n and n, here too. The difference in probabilities that A wins the CCA game and that A wins the RCCA game is bounded by the probability that a valid query occurs in the CCA game. Yeah. And the third lemma that we prove is that this probability here is negligible. Okay. So let's prove first 5.5 from these three lemmata. Okay. So let A be fixed but arbitrary. Then what we need to analyze is the CCA advantage of A against our authenticated encryption scheme, which is the difference in absolute value that A wins the CCA game against pi minus 1/2. This is, now I just squeeze in this probability here, subtract it, add it, then use triangle inequality. So that is the same as the probability that A wins the CCA encryption scheme minus the probability that it wins the RCCA game plus this thing minus 1/2. Okay. I just added 0. Always a good idea at some point to add 0. Or maybe I just write it in here because it's quite useful. I have it here. So probability okay. Now I use triangle inequality. Nothing has it, just triangle inequality. But this here, we know is upper bounded by this thing here. Huh? So this is upper bounded by the probability VQA pi of n being 1 plus this guy here. Huh? So here I used, this is 5.9. Now by 5.10, this is negligible. By 5.8, this is negligible. So here this is negligible, 5.8, and this is negligible, 5. And as we know, the sum of two negligible functions is negligible itself, so we are done. If we can manage to prove these three results here. Yep. Good. Now we do this thing. Actually, the nice thing about the sequence of this lemma is that the proofs also are increasing order of complexity of the proofs. This is simple. This, once you know the difference lemma, is simple. This one is work. Can I erase the board? So let's prove lemma 5.8. Okay. And the proof uses that pi is CPA secure. Recall it's an authenticated encryption scheme, so it's CPA secure and has unfoldable encryption. Here we only use the CPA security. So let A be fixed but arbitrary against pi in this game here. Oh, A. Sorry. Now from A, construct A prime against pi in the CPA game against pi. Okay. How do we do that? So A prime on input 1 to the n and all these things, we just simulate A. Okay? And A prime playing also Challenger for, so it simulates it, so it has to answer the queries of A itself, maybe with the help of its challenger. Okay, and recall the challenger in the CPA game for A prime will only answer encryption queries. But we are in the, so in the RCCA game, the A can ask decryption queries. But those are always answered with the failure symbol. So that can easily be done by A prime itself. Right? So that's what we do. So simulates A, answers encryption queries using its challenger, answers decryption queries with the failure symbol. It's great. I mean, this is exactly like this game here, right? The simulation of A is perfect. It gets exactly the right answers back. The answers are as in the RCCA game. So what we can easily conclude is that the probability that this is 1 here is the same as the probability that this is 1 here. Right? Or the probability that this is 1 is the same as the probability that this is 1. But since now we subtract 1/2, it's CPA secure, so this must be also negligible. And we are done. So that I don't write this down, but it's, you know, there's nothing that's really happening here. So that's what I meant in the game hop. We replace the CCA game by this RCCA game that we can easily analyze. Okay? And you see that this is now really easy to analyze, given that we assume that pi is CPA secure. But now we have to analyze, and this is where the work comes in, we have to analyze this here, we have to prove this here, and then we have to analyze and prove this event here, the probability for this event, and this is done in lemma 5.10. Okay. Yeah? So now we would like to go to lemma 5.9. I erase this. Oops. And the proof of lemma 5.9 is a simple application of this so-called difference lemma. So let me first explain the difference lemma, then we apply it, and then we prove it. Or maybe I explain it and prove it, because then you see where it comes from, and then I apply it. Okay? So the difference lemma says the following. Assume that we have 3 random variables, W0, W1, and Z, over some probability space. So we have the probability space, the space of elementary events. And we assume that for each elementary event, if W0 is 1 on that event, so it evaluates to 1, and Z evaluates to 0, then on that event also W1 evaluates to 1 and 0 evaluates, Z evaluates to 0. And also the other way around. So this combination of two things here is the same for both W0, W1, and this Z. Okay. Clear? Yeah?
What does this equivalence?
Yeah. Okay, let me, so.
I mean, we sets on both sides, right?
No, you have a function. You have functions. These are all go from some probability space omega to 0, 1. Yeah? What I mean is for all elements omega in this capital omega, we have W0 of omega is 1 and Z of omega is 0 is equivalent if and only if, what do I say? Then W1 of omega is 1 and Z of omega is 0.
Okay, so W0 equals 1 is not the pre-image of 1 intersecting
No.
with. Okay.
No, it's really, what I really mean is this, for all elementary, events, this is 2. Okay. So if on an elementary event W0 evaluates to 1 and Z evaluates to 0, then W1 evaluates to 1 and Z evaluates to 0, and vice versa. And then what we say is that, then what we can argue is then if the difference in probabilities that W0 is 1 minus the probability that W1 is 1 is bounded by the probability from above that Z is 1. Okay. So we also have on this thing here, we also have this probability, right? PR is from omega to 0, 1. Right? And then, right, so then this, if you the probability of W0 is 1 is simply the sum over all omega in capital Omega probability, the sum over all we sum up over all events where this evaluates to 1. Yeah, and similarly for this year and for this year. That's why I said that they all are over the random variables over the same probability space. So it's all over omega with the same probability function. Okay? In our case, these omega correspond to the random bits in the experiments. And they are all chosen uniformly at random, independent and uniformly at random. Okay. So maybe I first prove this lemma here. How you can see this. Okay. I erase this because I need this space for, sorry. Okay, we do the usual thing actually. It's So what we do is the probability W0 minus the probability is 1 minus the probability W1 is 1 in absolute value is the same. Now I add, partition both things into disjoint sub-events, namely z being 0, z being 1. So this is the same as the probability W0 is 1 and z is 0 plus the probability W0 is 1 and z is 1 minus the probability W1 is 1 and z is 0 minus the probability that W1 is 1 and z is 1. Yeah. Now, this condition here implies that these two probabilities are the same. Right? They happen on the same set of events. So if you remember, then the sum of these events, or the probabilities of these events, just cancels. Right? So this and this cancels. So this here is the probability of W0 being 1 and z being 1 minus the probability of W1 being 1 and z being 1. Now we condition on these things, and also we write this in conditional probability. So this is the same as the probability W0 is 1 condition, z is 1. I'll write this later on. So minus the probability W1 is 1 conditioned on z is 1. And in both cases, I have to multiply this by the probability that z is 1. That's a common factor that I can pull out here. Okay. Now, this certainly is, this is a difference of two values that lie between 0 and 1. And I take the absolute value. If you take the difference of two values between 0 and 1, the difference lies between minus 1 and plus 1. The worst thing that can happen is 1 is 0, the other is 1, and vice versa. So this here is less than 1, and then we are done. We have this. So this condition here allows us to cancel these two events, and then we just only have to look at the other thing. Yep. So what this says is we want to analyze this probability, the difference in this probability. We know that if this event z does not happen, then the two things are equivalent, and then we can analyze this by the difference. This is different by this probability that the event z happens. Okay? Oops, wrong direction. Now, we want to use this in this case here. So obviously, we already know what things are going to be, right? This is W0, this is W1, this is Z. Okay? Okay? Z being valid query occurs or not, does not occur. Z being 0 means valid query occurs. Right? This here is Z, this guy here. Yeah? And remember, here we are. It's 1 if A asks a valid query, say in CCA. Okay. Or we can, yeah, and valid here, that says that it on a certain randomness, it asks them. On a certain randomness, it asks them, say, in one of these games. And it's 0 otherwise. But if this thing never happens in the CCA game, right? Never asks on things, well, then the two games, RCCA and CCA, are the same. Because we always answer the decryption queries correctly with the failure symbol. Right? The whole game is, in both cases, then, if there is no valid decryption queries, actually in the CCA game, the two games are identical. Because we answer in the RCCA game with the correct answers in the CCA game. So we actually, in that case, we have this condition here. If there are no valid queries in the CCA game, the two games are identical. And hence, we have these things. And that we only need it in the CCA game, because then the first query is decryption queries answers correctly, the second, and so on and so on. So the two games will always be the same. Whether it's outputs, the B and the B prime, the output of A is the same in both games then, or with the random choices. Okay? Yeah?
Do we have an invalid symbol in the CCA game?
Yeah, absolutely.
Okay.
Yeah. I mean, this is the way this encrypt and authenticate is defined, right? You have to go back all the way to the definition of such a thing. If there is an if there is an invalid ciphertext, we do that. So if I go back to here to the encrypt and authenticate, yes, of course. If the verification of the ciphertext with the tag is not valid, then we'll just output invalid.
Yeah, and our scheme
is an authenticated encryption scheme. So it really does use these things. But always, if I think, say, authenticated encryption scheme, always think of this here, right? But any authenticated encryptions, we just allow these things, okay? And this is like the blueprint for an authenticated encryption scheme. Yeah? Okay, so it remains, oh, that's a short one. Okay, good. So now it remains to prove, so let me, or maybe I just go back to this once more. So we have the difference lemma, why do we, so here, when we apply this, it's really, we have, this is W0, W1, Z, and the probability space is the random choices made by A in, say, the CCA game, or over these things, and then the events are just whether it outputs the correct B or not, and here whether it poses a valid query or not. Okay. Okay, now we have to analyze this guy here. And it's always good if you do a complicated proof of a theorem. Well, actually, if you could do a complicated proof of a theorem, you first have to formulate the theorem. But once you have done that and you do the proof, always think, yeah, did I use all my assumptions in the lemma already? Is there something that I didn't use so far? And then something seems to be fishy, right? Either you don't need that assumption or the proof is wrong. Right? In our case, so far, I did not use that pi has unforgeable encryptions. I used CPA security here. I didn't use anything here. I just used the difference lemma. So I better use unforgeable encryptions, or you should not believe that I presented you a valid proof. Okay? And this is really based on the assumption that pi has unforgeable encryptions. So okay, so I will relate this here to the probability that an arbitrary, fixed but arbitrary adversary A wins the unforgeability game against pi. Okay? Okay, so relate. So from what we do is A is as usual fixed but arbitrary. From A construct A prime against pi in game enc forge. Okay. Show that the probability that enc forge A prime against pi is 1 is upper bounded, is an upper bound on 1 over q to the n times vq A pi, oops, sorry. Yeah. Probability vq A pi n is 1. And recall, Q of n is, as we said here, is the number of decryption queries that A poses. But A is a PPT. Yeah? So this is a polynomial. This here implies that this is negligible. Yep. So what I can do here, if I rewrite this, I know that this is upper bounded by a negligible function times a polynomial, and hence is still negligible. Yep. Okay. Remember, negligible times polynomial is still negligible. So it basically remains to prove this here, using constructing this A prime and do this stuff. Okay? Yeah. So here we go. So A prime from A. So we have our fixed but arbitrary A. Now we define our A prime. So in the first step, A prime chooses an index J prime in the set 1 through Qn. Index guessing. Okay? It tries to guess the first time A in the original game has a valid decryption query, poses a valid decryption query. It tries to guess that position. Okay? Then it simulates A on 1 through to N. When A asks for an encryption of message M, A prime is an adversary against in the unforgeability game. It has its own challenger. So the encryption queries, it can just forward to its challenger and get the correct answer back. Remember, in the Engforge game, you have the challenger that answers encryption queries for you. But then you have to come up with a new ciphertext that is still valid. So you can forward your challenger, A prime can forward its challenger for the encryption of M and output it to A. Good. Now, when A queries for decryption of ciphertext C, then if this is the J star decryption query, we simply output C. A prime is against the ciphertext forging game. So its goal is to output a ciphertext that is valid. Right? So now it guesses, so the J's query will be the right one. There the A will query or will pose a valid decryption query. So it outputs C. And in all other cases, it outputs the failure symbol. Maybe we go back to the unforgeability game. This is all the way back here. So here, you remember, its goal is to output a ciphertext C that is valid, and that was not one of the messages for which it queried its encryption oracle. And now we do that. Okay, I assume that J star is the right one the first time that A really outputs a decryption query. And so what can we say about this guy here? Well, so there are several observations to be made. The first observation is if A prime guesses the index, this J prime, J star is really the first the index of the first valid query of A, then up to this query, the view, the answers that A and A prime get, or that A gets in the simulated thing, is the same as in the CCA game. Right? Because, why is that? Because, so J star was now really the first valid decryption query. So all the previous ones were invalid. And they are in the CCA game, they are answered with the failure symbol, and in this simulated view of A, they are also answered with the failure symbol. So up to that point, everything the simulated A sees is exactly as what the real A sees in the CCA game. Huh? In particular, all the queries that it poses up to that point have the same distribution. After that point, I don't care. Because after that point, I already have my answer. What this thing does afterwards, I don't care. But up to that point, it's the same, and I use that to analyze the whole thing. Okay, this is important to see that. And remember, we always, if you simulate something and want to analyze it, we always have to make sure that the distribution of the answers that it gets is the right one, is the same as in the original experiment or game. But here we have that up to this point. After that point, and that's the difference from what we have seen so far, after that point, things deviate, but we don't care, as we'll see. Okay, so now the first observation is, it's simple. It's nothing to do with my A prime. It's just, as I said, I can partition this event that the valid query occurs in the disjoint sub-events that the J's one is the first valid query. That's a disjoint partition. Right? And hence, I can just write this probability here as a sum of these probabilities, disjoint sub-events that cover the whole event. No? That's easy. The second one is the one that we really need to prove. Okay. Yeah? So now let's write down this probability . And this probability, this is A prime, yes. Let's go back here. This, I claim, is larger than the following sum. It's larger than. So let's view this J star here is a random variable that can take on these 1 to Qn values. Okay? It's just a name for a random variable. So it's, and I claim that this is larger than the probability that I pick as J, the J as this value for the random variable J star, and I have VQ A pi J n is 1. So what does that mean? This event means that my J star is J, and J is really the first valid decryption query of A. And if that happens, then I win. Maybe there are other events where this guy wins. But I don't care. At least in these events, he wins. And hence, this probability is at least as large as the sum of these probabilities, because those are disjoint events. J star has a fixed has one value, okay, not many. Yeah. Yeah. Okay, and we also need this observation here, because up to that point, this view is really the same. The simulated view is really, I should have written here that in the simulated view of A, this is the first thing. But the simulated view up to that point is the same as the real A, because it all gets the same answers. Okay, but now it's just manipulating the sum here anymore. But this is important then. Here I really use this observation already, because in the simulated view and then the real view of A in the real game, the two events happen with the same probability, the first thing. Okay, now we can just rewrite this. The sum of all j from 1 to qn. Notice that the guessing of the index has nothing to do with what A sees. Right? This is independent. I pick an independent index, independent from the rest of the choices that are made. So I can rewrite this and as a product. So this is a product. J star is equal to J times the probability VQ A pi J n is 1. So this is independence of A. And now we are almost done, because this is obviously 1 over Q of n. So this is 1 over Q of n times J from 1 to Q of n, probability BQ A pi J of n is 1. But now we can use this observation here to argue that this is 1 over Q of n of the probability VQA pi of n is 1. And we are done with the proof. Yep. Okay. Yeah. And we have proven everything. So the important thing is at this point here, where we need that in this game here that this guy plays, up to the point where there is a valid decryption query, everything is in the real CCA game. So in particular, the probabilities for these events are the same in the simulated view as in the real game. After that point, I don't care. That's why I have to pick this point, guess it, and at that point I need to produce an output that's useful for me. In this case, the useful output is simply the query itself. Right? And that is a useful output for me because that event is exactly defined that this output at that point, the query, is a valid query. And that's exactly the goal that A prime has. Output valid decryption queries. And why did I make this assumption here? Where in this whole proof did that come up? Why did I have to make that? Yeah?
Otherwise, we would not necessarily win if this event happens because we would output a ciphertext which we already queried for.
Yeah. This assumption guarantees that this is always satisfied. If I don't make this assumption, you have to define the event VQ slightly differently. Maybe that's a good exercise to do that, formulate that in the definition of this event. And then also slightly change A prime, the definition of A prime. Okay, so finally we made it. We have constructed an authenticated encryption scheme that is CCA secure. And on the way to constructing this, we have seen several different and important things. So first of all, encrypt and authenticate. It's an incredibly important technique. Most things in practice want both things, confidentiality and authenticity, so they just use encrypt and authenticate. Sometimes they don't do it exactly in this form. Sometimes these things are merged to each other much stronger, right? For reasons of efficiency. Right? Sort of while computing the encryption, you also encrypt already the tag, so that you don't have to go over these things twice. But we also saw two important proof techniques, namely game hopping, the difference lemma, and this index guessing. Both will come up in the course again. In particular, this index guessing will come up again. The game hopping is also interesting. In fact, you should think about that you already saw game hopping. I didn't call it that way because it's easier to do it differently and don't use a difference lemma because it would be too easy to actually recognize it almost. But you have done that before. You have done that before twice, actually. Okay, so but what we have we achieved so far? Let me do that together. Right now. So what we've done so far, if you go back to the very beginning from our construction. So we first constructed eavesdropping secure encryption schemes from pseudorandom generators. Yeah? Then we constructed CPA secure encryption schemes from pseudorandom functions. Then we constructed secure message authentication code also from pseudorandom functions. Then we constructed authentication encryption schemes from pseudorandom functions. right? Why did we do that? Well, we just used the CPA secure encryption schemes. Take the one using pseudorandom functions. Take a strongly secure message authentication code. We know that we get one from pseudorandom functions. So if we take those two things, combine them in authenticated encryption, the way we did that, encrypt and authenticate, we get an authenticated encryption scheme from pseudorandom functions. Just assuming that pseudorandom functions exist. And finally, what we did today, theorem 5.5, was we constructed CCA secure encryption schemes from pseudorandom functions. Remember, I said what we want to do is we want to build things from general assumptions. So our general assumption here is pseudorandom functions exist. Well, we can pin it, we can simplify our assumptions a little bit, well, quite a bit actually. So what do we need to construct pseudorandom generators and pseudorandom functions? Can we make that a little bit easier, or can we reduce that to the assumption that simpler objects exist? And what one can prove is that if one-way functions or one-way permutations, actually one-way functions are sufficient, exist, then pseudorandom generators and pseudorandom functions exist. And the way one does that is, and I will outline that a little bit in the next lecture, but not in real detail, is from one-way functions one can define so-called hardcore predicates, one-way functions with hardcore predicates. From one-way functions with hardcore predicates, one gets pseudorandom generators with expansion n+1, just one more bit. But then one can show that if we have these things, we can actually construct pseudorandom generators with polynomial expansion. And once we have these things, we can actually say, then we can construct pseudorandom functions. So it all boils down to one-way functions must exist. And here I only proved this direction, stated this direction, but what you can also prove is that if pseudorandom generators exist, if eavesdropping secure encryption schemes exist, then pseudorandom generators exist. If pseudorandom generators exist, then one-way functions exist. If CPA secure encryption schemes exist, then pseudorandom functions exist. If pseudorandom functions exist, pseudorandom generators exist. If pseudorandom generator exists, one-way functions exist. So together that shows that secure symmetric encryption schemes exist if and only if one-way functions exist. So these are the real objects that we need to assume. Without them, with them, we can construct secure encryption schemes and also message authentication codes. Without them, forget it. So next time I'll tell you what one-way functions are and go a little, but not in much detail into these things. Just tell you basically, I just don't want to go into the details there. But I will tell you what one-way functions are and also one-way permutations, because those are the things when we go to public key encryption, we need those things to define those things anyway. Okay, so that's the two things to take home for today. So secure symmetric encryption schemes if and only if one-way functions exist. Authentication and encryption implies CCA secure. Encrypt and authenticate gives this to us. Game hopping and index guessing, those are the two important techniques that we'll meet again in this course. And that's it for today. Any questions? If not, next Thursday is a holiday. The next lecture is the Monday after, early in the morning. It's one of these additional lectures, but we'll stream that and take the videos anyway. Okay, good. Thank you.